welcome to Desk of Lady Ada.
Hey everybody, and welcome to my desk. I'm the Lady Ada, and this is my desk. And every single time we broadcast, we do a live show where I talk about some electronic engineering I'm doing, and hopefully tie it into your life and make you care about it. And then maybe we'll be friends. With me is also Mr. Lady Ada on camera control. Thank you for. So if you're like, who is this person that she's speaking to?
Yeah, I always
It's not
ask,
like a snuffleupagus. It's actually you.
I always ask, who is this person and what does it mean?
Deep.
Yeah.
Intense. And of course, you can ask live questions.
Yeah, in the chat rooms.
The chat rooms. And,
we're on Twitch, we're on Facebook, and we're on YouTube Live.
Yeah. Hopefully the questions are somewhat related to what I'm working on, but
Yeah.
if you really just have a burning engineering question, like, shoot, why not? Just go for it.
Yeah, if your project is burning,
Yeah, you will.
we'll
I'll
probably tell you to
water,
more capacitors.
unplug it.
You need a capacitor. Okay.
Okay.
What are we talking about tonight, Lady
So
Ada?
tonight we're going to talk about the MAX30100. So I got a huge backlog of sensors. I go through these like sweeps where I look online and I check out what are the cool new chips and the cool new sensors that are available out there, because companies are constantly coming out with sensors. And then what I do is I end up designing a whole bunch of boards, and then like 3 months later I'm like, oh yeah, I should like totally finish that design. So the MAX30100 is the one I'm going to show a little bit off today. And can we go to CompuCam? I'll show off the page in the datasheet. So this is the web page from Maxim Integrated, so they're the ones who make this, and it's a pulse oximeter and heart rate sensor IC for wearable health. Basically, it's a little sensor that if you've seen like smartwatches, on the back of them they have these LEDs and like these glass bits that you press against your wrist or against your hand or your finger, or you go to the doctor and they put a clamping thing on your finger to measure your heart health and your blood health. This is the sensor basically that's used inside. A MAX30100 is an all-in-one sensor. It used to be you would actually DIY it by having separate LEDs and sensors I'll show how that works, but this is an all-in-one chip, and I thought like that's kind of cool. It's an all-in-one, might make it easy for people to try this out. And not a lot of pulse oximetry and there's a couple heart rate sensors, but I haven't yet seen a maker pulse ox sensor. So if we could get this working, that would be really neat, because it would be a new kind of sensor. So let's look at the data sheet, because I actually have a pretty nice diagram of how this works. So normally, I guess they're expecting you to use your finger when maybe you have a phone, and it would have it's glass on the front, and there would be a little section where the glass has no ink on it, so light can go through the glass. And then when you press your finger to it, there are two LEDs. This is a 2 LED symbol. There's an IR LED and a red LED, and they flash light at your finger. And then that light gets bounced off, and there's like one that's kind of dark and one that's kind of grayish. So that's the two different light beams coming back. And then there's a photodiode that detects that light, both types, and an analog digital converter that then reads those signals, and then you can do processing on it to read your heart rate and pulse oximetry. So this sensor has a red LED and an IR LED, and these graphs show the sensitivity to light. So if you are shining red light off of your finger, it will be very sensitive to Hebe, I guess the metallic hemoglobin-esque thing, the thing that's red in your blood. And then red is more sensitive to, is more sensitive to blood that's not oxygenated, and it looks like IR is sensitive to both. And so if you have both of these signals, you might be able to like subtract them or do some math to figure out when the oxygenated blood is peaking and when the blood rate in general is peaking. So we'll kind of see a little bit when we graph this how one is definitely more sensitive to blood than the other. I don't have a pulse ox algorithm, but apparently Maxim publishes one, so I might be able to get one and integrate it in a future show. But that's basically what it does. It bounces light off of your finger, and then depending on how that light is absorbed and reflected, the sensor will tell you how much blood is coursing through your finger. I mean, there's a couple of cool, wasn't there like an iPhone app where that you could actually point at your face and it was sensitive enough that it could see how the redness in your face changed with your heartbeat?
Yeah, I have an app, but I still have it. It looks at you and it tells you your heart rate.
Based on your face, because it flushes just a little bit,
Yeah,
the redness.
And my Apple Watch does that too. I think I got it down to like 40 beats per minute or something. It was really low.
Yeah, also your no.
What?
No, it's like if you can just control your face blood.
I like to control my face blood.
Like, what kind of ninja skill is that?
It's just a face blood skill.
Face blood. Okay,
Yeah.
so this sensor, we actually, in a previous show, made the circuit board for it. And I'll show that off, because why not? Breakouts. Sensors. You can see all the things that we have done and may do at some point in the future. Sometimes people comment on YouTube and they're like, hey, I see that you have a PCB for a thing. You should get that thing done.
Enhanced Section 7.
I know. So this is the PCB that we designed. Oh, hold on. This is a little smaller. So this is the sensor designed on the show last time. And it's just a basic breakout. This is the sensor. There is LED aperture here, and I think this is where the sensor part is. There's pull-up resistors for I2C. This sensor is read via I2C. It's not an analog sensor. It's not an SPI sensor. It's I2C, which I really like, because that means it's going to be usable across a wide range of microcontrollers. I'm not a huge fan of I2C, as longtime viewers may be aware, because I'm annoyed by the inconsistencies in implementation of I2C, repeated start and clock stretching and different ways to read and write registers, and like Scilab's always just like crazy shit with I2C, and it's like ridiculous, and some have like different size registers. But for the most part, you know, it is the most common interface that's available to any microcontroller or microcomputer. Raspberry Pi has it, BeagleBone has it, Arduino has it, you know, Dragon Board's going to have it. Every single microcontroller and computer, even laptops have I2C. It's through the HDMI port, which is a little bit weird, but they do have, you know, in a way, I2C. It's just like the most universal sensor interface. So I kind of like that compared to a DIY version where I actually pulse the LEDs myself and read the analog signals. And then I have a dual LDO, a low dropout regulator, because I need both 3.3 volts, that's the I/O voltage, and 1.8 volts, which is the core voltage. For some reason, they decided the sensor core ADC runs on 1.8 volts. So that's that. But the LEDs, the IR and red LED, require 3.3 volts because, of course, they have a 2.2 volt forward drop. So that's the circuit board. So we got that made, and we put that together last week. So I've got that. And then the way this works, the sensor is actually pretty straightforward. Here's I2C, great. So this diagram is in every data sheet known to man. Even data sheets that don't have I2C, they just put that in there, why not? So you've got an LED that you can change the pulse current. You can also configure the pulse, not like heart rate pulse, but the LED pulse, how bright it is and how long it goes for. So yeah, IR LED, red LED, and then this sensor, and then there's like there's a temperature sensor inside as well, so you can, because apparently with pulse ox you can do better calibration with temperature. There's LED drivers because these are high current, and then there's some basic digital filtering, and then I2C. Now again, the digital filtering isn't advanced. It's not going to pop out heart rate, but it will do some basic filtering for you. So at least you're getting the true signal out. I guess, you know, it might filter out for like 60 hertz noise or 50 hertz noise, because that would come out from like ambient. It does an ambient analysis for you. Yeah, ambient light cancellation and some sort of filtering. Maybe you can have it do low pass filtering. I don't know. I haven't dove deep into it. Both LEDs can be configured from 0 to 50 amps, 50 milliamps each, which is pretty high. 50 milliamps is pretty high. Usually I've seen pulse ox LEDs run about like 7 milliamps. It's a trade-off. You know, higher current might get you better results, but of course you're drawing a lot more current. And 50 milliamps, even in a spike, is nothing to sneeze at. That's a bit of current, especially if you're going to have two LEDs. It's 100 milliamp peaks. So if you have like a watch or a small wearable device, you'll have to judge whether you need to use that much current. There's some ambient light cancellation circuitry, who knows how that works, and a 16-bit ADC, and then some sort of discrete time filter that they don't really tell you about. And there's actually not that many registers. This is it. This is the entire register list. There's some status and interrupt levels, and then there's configuration. You can basically configure the LEDs. Some, third of these are reserved. You can read the temperature from these two. And then there's 2 for part revision and ID. And so really the only 2 registers you really mess with are mode configuration and then this SPO2 configuration. And then you read data from the FIFO. So what's interesting about this sensor is they try to make it a little easy on you in that there is a FIFO, a first in, first out chunk of data. There's a little bit of RAM essentially inside of these registers. And instead of reading the data, because you'd have to make sure you pulse the data from the ADC, or read the data from the ADC exactly at the right time, the chip takes care of reading the ADC and pulsing the LED and all that for you, and collects up to 16 samples and puts them in this stack, and then you can read all 16 at once. If you want to read one at once, it'll do it like a ring buffer. So as you read one measurement off, it'll go to the next one, and then you can read 2 if you want, and it will just keep going forward as you read data off. And you can set the interrupt to tell you when it's time to read. That's kind of nice. I mean, it's not how a lot of sensing that we do. Like a lot of the sensors that I work with, accelerometers and gyroscopes and such, you usually just read a measurement once. But with this, you actually have to make sure that you measure exactly at a certain rate. And you can't vary that rate. You really want it to be as consistent as possible. And having it take care of that for you is kind of nice. So you just push data off the stack when you're ready to read. So you can go through this data sheet if you'd like, but I've sort of started on a library, and I'm not going to write the whole thing because this took me a couple hours. But essentially, I've got the register table all written out. So that's like the first thing I do. And then you do type defs for all the different sample rates. So you can sample at different rates. Of course, the higher the sample rate, the more data you're going to get, but you need a lot more memory to store that data. And we'll do the math. It actually turns out that you need quite a few seconds of data. So once you're getting into more than 200 hertz, it adds up quite quickly. You can also change the pulse width. The pulse width will also affect the effective bits of resolution you get from the ADC. When you read, when you pulse the LED only 200 microseconds, you can only get 10 bits of ADC precision, because the ADC does successive approximation. It will take some time to get that measurement. So if the pulse width is too small, it doesn't have enough time to do a measurement that successively approximates enough. So you'll need to have a longer pulse width for more precision, but again, more pulse width of LED, higher current. So all trade-offs in power and engineering. And then I've written a lot of sensor libraries. I wrote this a lot like every other sensor library. When you call begin, it checks the part ID, make sure the part ID is what you expect. So that way you know that it's the correct component, because you want to make sure that the chip is just connected at all. And if you can't read the right part ID, it means something's not wired up with I2C, so you do that. You do a reset, and then you do an enable of the interrupts, and you reset the mode configuration. There's a bit that you set to reset. And then you can read the temperature if you'd like. And basically you just tell it, hey, I want to do a temperature reading. You set a bit in the mode config register. That's done here. Max mode config temp enable. You write that to the register, wait until that bit's cleared, and then you can read it from the 2-byte register called temp data int. And then the code that I wrote in Arduino, which interfaces with this, I didn't make it use the FIFO because I actually was having a little bit of issue with that. I was trying to figure out the FIFO size and how much to read, and I wasn't quite getting the data that made sense to me. So I basically just did a very simple read 1 byte at a time. But I just made this object, and then I actually am running this on an ATSAM-D21, and the reason I'm using an ATSAM-D21 is because I need to get 5 seconds of sample, because your heart rate is like once a second. So if you want to get any reasonable amount of data for you to manipulate, you need like 5 to 10 seconds. And each sample is 2 bytes. And then, like, let's say your sample rate is 200. So let's say you want 10 seconds of 200 samples a second times 2 bytes per sample. And that's just heart rate, not pulse oximetry. So that's 4K. So that's a ton of memory. Like it adds up very, very fast when you have to measure multiple seconds of data and store it in RAM. Like if you have FRAM, that might be fast enough for you to push the data to, but it's very nice to keep it in a RAM buffer instead. And so if you can imagine, all right, like if you're doing anything more than that, like the sensor can go up to 1 kilohertz. So 1,000 samples per second times 10 seconds times, let's say you're doing heart rate and pulse oximetry, so it's 2 bytes, 4 bytes total per sample, and now you're talking about 40K. So that's like okay, you actually can't really use a microcontroller anymore. Now you're heading into a Raspberry Pi or a BeagleBone would be necessary, or of course a larger microcontroller like a Cortex M4 with 256K of RAM or something. But this is way beyond what an Arduino Uno can do. So that's a little bit of a downer. I kind of wish that this would be able to work with an Uno, and I think you can kind of basically do some basic heart rate stuff on an Uno by doing the lowest heart rate and only 5 seconds. So if you do only 50 hertz and then 5 seconds and times 2 bytes, okay, 500 bytes. So that you can do on an Uno, but anything more, like I think you can do basic heart rate sensing, but if you want to do pulse oximetry, I think that's actually going to be something you need to use an ATSAM-D or like a DUE or something to measure. So that's a little unfortunate, but that's okay. Well, we have chips. Is there any questions from people?
No, keep going.
I just had a huge ramble. Okay, so this is my test code. I begin. I say I'm printing a test. I was doing some checks where I'm trying to figure out what the I2C buffer length and all the different chips are. Turns out that the buffer size is 64 bytes on a ATSAM-D. That's important because if you do want to read the entire FIFO, it's 64 bytes, and on Arduino Uno, I think the I2C buffer is only 32 bytes, so you couldn't read the entire FIFO at once, even if you wanted to. I try to tell whether the sensor is even there, so I basically query it. Is that ID register reading the right number? If I find it, I'm going to set the IRQ pin to be an input because I'm going to use that, and I'll set the sample rate to 50 hertz. Again, you can change this to anything, but for this demo, 50 hertz is plenty. And then I have a little thing that also tests my function to get the sample rate and print it out. And then I'm going to do the maximum pulse width, so 1600 microseconds. That means I get, again, the most precision for the readings. So even though I'm only reading at 50 hertz, I'm going to get a lot of precision to my readings, even if they're not happening as often. And I'm going to set the red LED current to 30.6 milliamps because I don't know. This is the LED that's used for pulse oximetry readings. And then this LED is for heart rate readings. I mean, you use both for pulse ox, but if you're only doing heart rate, it doesn't use the red LED. And then I just print it out so I can verify my readings. This is just like debugging stuff. Like as I wrote the functions for getting and setting, I want to have a test case, right? So that I can make sure that my get and set are correct, because it would be very, very frustrating for a user if they thought they were setting the LED to be 3 milliamps and it's actually 30. Like a simple typo can really trip people up. So when you're writing a library, having a black box test is pretty handy. And then I just start read. So start read is actually what kind of kicks off the reading of data. And once you say start read, the sensor will immediately start filling up that FIFO. It will not wait for any other messages. It won't stop until you tell, basically it doesn't stop until you tell it. It just reads every 50 hertz or whatever you tell it to over and over again. It will fill the FIFO. And if you don't read the FIFO in, it will start dropping the oldest messages. So only the most recent 16 readings are in that FIFO. And then I'm going to basically fill the entire buffer and then print it out. So it's possible that at some point I could read the data and print it out simultaneously, but you just have to make sure that you time things right so you don't end up filling the FIFO and you print out the data and interleave it. So I thought until that gets done, I'm going to just read 5 seconds worth of data, which is 50 hertz times 5, 250 data points, and then I'll print them out. So here I just wait till the IRQ line is brought low. So it's a low signal on that pin from the chip says there's data ready. If some data is ready, I will read 32 bits out of the FIFO data register. And the top 16 bits, 2 bytes, is IR data. And then the bottom 16 bits is read. That's how it works. It's basically, you have to read 4 bytes, and then you cut them in half, and 16 bits are one, 16 bits are the other. And then once I have completed reading all of the up to max samples, I will print them out. So that's it. So let's try uploading this to my M0. Oh, and then we can go to overhead cam.
Do you want a split screen, or what do you want?
Yeah, split's good. I can show off this sensor. So here I have the sensor, and this is the breakout board itself. So here is, I think these are the IR and red LEDs, and then this is the sensor in here. And then we just have the supporting circuitry and then the breakout pins over here. And this is a prototype, so it's green, but the final one will be blue. And then I have it hooked up to a feather. And this is an M0 feather. It's just an ADA logger version. I'm not using the micro SD card, but it's there. And then I have this wired up to I2C, and then the IRQ pin, and then power and ground. So this is set up. So when I boot it up, it says, okay, I found the, oh, can I go to the split screen? Sweet. I boot up, it says, okay, I found this Max chip, and I'm going to sample the data at 50 hertz. I'm going to make a 1600 microsecond pulse width LED. I have 30.6 milliamps from red LED and 11 milliamps from IR LED, and then it reads the data. And since my finger is not on it, the data is very, very small. It's like 16, 24, 28, 30. It's like these super low numbers, because there's no light reflecting back. It's the light is just emitting from the sensor. There's no finger for it to bounce that light off of. So it's going to keep saying 20, 40, 12, or whatever. It's just getting ambient light sense. And it's actually doing a pretty good job of rejecting light that isn't from that pulse of LED. It could be that it samples a little bit before and after the LED pulse and then subtracts it. So any ambient light is not counted. And then let's put my finger on the sensor. And you'll see the data jumps up very fast. So now it's like 9,000, and it's hovering around 9,000 or 8,800 or so. And then when I remove my finger again, it goes back down to like 12. So the only problem is it's very hard to say what's going on here, because you're just looking at numbers, and there's 250 numbers, and how are you going to see patterns in it? So that's where I thought this is a good time to try out the serial plotter. And the serial plotter is a neat new addition to the Arduino IDE that lets you plot data. If you're printing out data, you could do this with processing, or a Python with Pi math. Oh, what is it called? I don't remember the Python math graphing library. You can use XGraph, all sorts of different graphing tools. But if you're doing some very basic data analysis, very, very basic, you can use the built-in serial plotter. So this plotter, just over time, it takes the last, I don't know, it looks like 500 lines, and then it graphs them. It figures out the minimum and the maximum, so that this is between 0 and 40. So you see, like, it's just kind of staticky noise between 0 and 40. And then if I put my finger on the sensor, you see it quickly jumps up because I'm now reflecting light off of it. And it looks like, okay, well, there's nothing going on, but it's a little bit bumpy. And then as the only thing about this plotter is you have to wait for it to normalize. But if we wait a little bit, and if I shift my finger, unfortunately, it spikes and kind of sets everything off.
So when you're ready for questions, let me know. We do have a few.
Yeah, okay, I'm actually not getting, hold on. Let me just make sure I didn't set this, because I should have this printing out IR data, and let me make sure I have this on heart rate only. I do, that's weird. See if I can get it to, it's one of those things, it was like totally working, and now it's like not totally working. Yeah, sure, what's the questions while I wait for this to get normal?
So the first question is, can this sensor be reliably used against other parts of the skin, such as your wrist and not just your finger?
I don't think so. I actually think it's really only good for fingertip sensing, because that's kind of, I think, the most sensitive part. I think wrist, you have a lot of motion, and it's also tough to get reflections. Apparently earlobes are really good too, but it's just tough to get my ear up against the circuit board.
Okay.
Okay. Oh, can we just show off the graph? So when you have your fingertip pressed properly, like, so you actually have to have your.
Maybe move that under there so people can see it.
Well, it's gonna. Yeah, unfortunately, when I move it, it's gonna freak out a little bit. If you really have to get the pad of your finger on it. This is a little bit of the issue. It's sensitive. You can't have it be near like the bone of your joint. It has to be right up against like the pad of your finger. And you can start to see there are patterny bumps. It's tough because there's quite a lot of noise in there, and like as I move, it's going to. Yeah, this is like, you actually can't do a live demo of this because you have to be super still.
Want another question?
Yeah. The problem is, I get distracted.
Okay.
Yeah.
So the way you've got it set up now, will only give you a reading every 5 seconds.
It will give me a reading every 5 seconds, and then what I will have to do is analyze those last 5 seconds to read out the heart rate.
Okay.
Because as you can see, it's like there is, actually I'm going to change fingers because my right hand is more useful to me. You have to get a lot of data, and then you have to do a lot of low pass filtering and also peak detection. Like, this is one of the things, it's like, it's not going to be nearly as nice as if anybody has ever done ECG. Maybe we'll do an ECG project at some point. When you put sensors on your skin with like gel and a really good amplifier, and you get a signal that's like this beautiful heart pulse wave, like it's perfect. But trying to measure pulse rate through your finger is tougher. So like you can kind of see that there are these triangular lumps. Each one of those is like, you can see my pulse, but it's like it's not what people think of as a pulse rate, where you would have like a lovely RTS V wave with the double bump. Instead, you get this like, it's a triangle wave, and you can clearly see like my heart rate is being detected, but it's just not this like clean and beautiful thing, and you're not going to get like heart. It's not like heart activity that you're getting. You're getting amount of blood in your fingertip, and so there is a little bit more work that has to be done to get this. And also, again, you have to be like perfectly still. Like if I move my finger, it gets all wobbly and I have to sort of start over. So as long as I'm perfectly still and I'm holding my finger right up against it, it works like very well.
Okay. Ready for more questions?
And earlobe works well because you're not moving your ears. Most people can't wiggle their earlobes.
Okay. Is this accurate enough to be theoretically applied for medical use?
This stuff is always used, yeah, it's used for medical use. Like I wouldn't design your own, but the sensors that are used for medical use are essentially the same as this, but it's more than one engineer spending a half an hour on it, like me. They spend a very long time getting data, making sure that the enclosure is like perfect, but pulse ox sensors are used all the time in hospitals to measure blood oxygen, as well as other sensors that they use. They use multiple sensors to get a lot of different data. But for hobbyist use, this is great because you don't have to get gel things and stick them on your body.
Okay. Is there any chance of a mood LED project coming up? So you would have, I guess, the LEDs change color based on your heart rate.
Sure. We actually have a pulse sensor that you can use now. It's an analog output, and you basically measure this analog wave, and it doesn't do like pulse oximetry stuff as well. It only does heart rate, but it uses a green LED, which I think is interesting. Apparently that works extremely well. And you could also get your heart rate out of that. And that sensor is very similar to this one. You could take that algorithm and probably apply it to this.
Okay. That's it for now. What else do you want to do?
That's pretty much it. That's just my demo. I wanted to show off this pulse sensor. Do you want to put your finger on it so you can see if you're alive or dead? No pressure.
Well, I'm dead inside sometimes.
Okay. So put the pad of your finger, like the meaty part, on top of this sensor, and then you press down. Okay, let's see. Okay, give it a second. We'll see how much blood you have. Okay, you actually got a pretty good signal too, so you can see the reflectivity of your heart. So bump, 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 bump. You know what I realized? I think this is actually upside down from, like, I think the lower the spike, that means more light is absorbed. So that means you have more blood. So this is like at the peak of your heart pushing blood out. But you're alive. Congratulations.
I knew it. Okay.
Okay, so maybe I'm actually gonna make a slight revision to this PCB, and then I'm gonna do a little bit of code just to do some low pass filtering. But I like the idea of having people, when they get the sensor, because we have to write a tutorial about the sensor, I'm gonna show them how to, put your finger and then put up the Arduino graph, and they'll be able to see the signal.
Well, there's one question, and I had a bad idea. So someone wants to know, is the noise in the wave that ambient light that the sensor is picking up?
I don't know exactly what the noisiness is. I think that there is just a lot going on in your blood and your skin, and so it's not easy to precisely sense the blood. Also, like your blood, it doesn't, it's not like, again, not like your electrical heart signal, which is like a perfect every single time, and you get this perfect way. I mean, of course, unless you have a heart murmur. With the blood, it's like, it's a fluid. It's gonna go slightly differently every time, and it's not going to, you're gonna get like fluid effects.
Yeah.
So I think you'll see like, peaks and valleys as, your hemoglobin increases and decreases, but you're measuring fluid reflectivity, which is already like a very noisy, messy system, not a beautiful electrical pulse with gel pads and a reference ground.
Okay. And then I had a bad idea. What if we got the cat, and the cat put his paw on there?
It's totally not gonna,
It wouldn't work at all?
His ear, maybe.
His ear? How would we get that on his ear?
I'm saying this is not easy. We could hold him, and we could hold it up to his ear.
What part of the sensor would we hold
like
up to his ear?
I mean, I could wire this with long wires, and then it would be easier. Let me.
This is a terrible idea, but I don't think.
Okay, so just hold on a second. Let me get some long wires.
But I feel like.
Science.
I feel like we kind of have to do it.
Yeah.
I feel like someone has to.
You're feeling just the pressure of existence. Okay, let me wire this up. So ground and V in. Okay. And then SCL can go to.
When should I go get them?
I need a little bit more time here.
All right.
So hold
I'll set up some
steady.
camera stuff right now.
Yeah, sure. I just have to get some very long wires.
Yeah.
Yeah, so this is going to be int.
Right, so, yeah, if you could just make sure what you're doing is underneath the hover cam, and maybe you can move the hover cam up. So
Yeah. No, we have to make cat clearance.
Yeah. All right. So I got a few cameras going on.
Okay.
So I got one that you'll be able to see.
Do you think someone's going to call the ASPCA on us? For cat abuse?
No. No, I think this will just be required now at the end of every show. People are going to say, take the cat's pulse. Okay, well, there was this rumor that MOSFET was dead, and we were just showing a picture of him, but it's because we can't bring him to the factory. Mm-hmm. But on Destiv Radiative, we see him here.
Is there MOSFET truthers? Okay, so what I did is I wired this up to be longer so that we could maybe adapt this to a cat. I'll have to hold his cat heart. I'll have to hold his ear with my finger if you want to try to measure.
Should I go get him now?
Let me, 1 second. Let me get this up and running.
Scary.
Shh.
I knew I was going to be doing this today.
Did you?
Yeah. Well, I think about it every day. Like, what electronics can we work on with cats?
Okay, so this is detected. And, okay, so it's measuring data, so I'm going to turn on the serial plotter. Okay, yeah, you can get the cat now.
All right, I'm going to go get him. I'll be right back.
All right, I'm going to clean up my wires.
Yeah.
Fetch the beast.
Ooh, the audience can hear me, but I'm away.
He's going to get the cat, don't worry.
Yeah. All right. So I got the cat. I found him.
The cat's not hiding. The cat's just asleep.
I found him.
That's what the cat does, like, all day. Okay, so let me make sure that this is working for me.
I feel like we're making live broadcast history here.
Yeah. It's going to be tough because we have to hold him steady for, like, 15 seconds.
Okay, I found him.
You found this cat? I don't think this is going to work out.
All right, well, here he is, everybody.
Okay.
And
so put him right here.
Okay.
Okay, he doesn't really want to do this. And then...
Oh, you're going to put it on his ear.
Yeah.
Okay.
Let's see what we get. Okay. Shh.
We're doing this, and I'll just hold him.
He doesn't really like it, but... Oh, no, see, the problem is he's moving. Don't move.
There he is. We got it.
Okay, wait.
This is happening.
Shh. Wait, no. Hold on.
Oh, look, we got something.
No, this is very difficult. Okay.
I saw something there.
No, you have to, it's because he's moving a lot.
Okay, he's sitting down now.
He's not nearly as reflective.
He's chilling.
He knows he's trapped. Yeah, this light is not...
Well, he absorbs all light. That looks like it's something.
No, that's just noise.
That's noise?
I think this isn't... No, see, that's like, there's nothing going on there.
All right, well, you should send an email to the manufacturer and say this doesn't work on our cat.
Yeah, well, you know what?
Tell me you want your money back. Maybe
he's not very translucent.
Maybe yeah.
You know, I thought maybe his ears would be a good way to measure. Whoa, later.
Yeah.
I thought his ears would be a good way to measure, because it's like, well, you know, his ears are like thin, so I thought maybe there's enough blood that would be detectable.
Yeah. All right. Well, I'm glad we tried.
Cat science is very hard.
Yeah. Hey, buddy. Bye-bye. Bye-bye.
Oh, weird. You know, it's not really working on me either.
Yeah.
Yeah, I don't know. Maybe I didn't.
Are we dead?
No, I wired this up right. I think you actually can't really move at all. You have to be like perfectly still.
Yeah. Well, cats don't do that.
Yeah, this is not very cat-like behavior.
All right. Then this is how science is done, folks.
Science is gross. Science is a little messy.
Yeah.
Science requires sacrifice.
Sometimes you just got to find your house cat and start putting electronics on them.
Yeah, what's interesting is like I'm not getting data out either. I wonder if I can't actually have this off of a breadboard.
We're discovering something.
And remember, like it was nice and spiky, and now it's like super noisy.
You know what? This is really good that we did this because a customer one day would be trying to do something like this, and we would be like, "Well, let's go get a cat."
What's wrong with your cat?
Yeah.
Do I have the interrupt at the right pin? Clock and data. Yeah, I don't know. Matt, you know, it works really well on a breadboard with, you know, pressing your finger, but maybe like holding it up doesn't work so well.
Okay.
Okay.
All right, everyone.
Well, that's science for you.
Yeah. Thanks for watching.
You always got this thing working, so I'm going to work on it some more. I actually want to redesign the PCB to be a bit bigger with more mounting holes because I think that, like, I can tell that you really need to have good attachment points if you want to read data from this. And then there's also another version of this chip, the 30102, which is a little more advanced. So I might check that one out as well.
Okay. All right. Well, thanks, everyone.
And if we can get cat science going, maybe I'll make a version that can clip onto an ear, and then we'll do that.
Maybe there'll be a new show, Cat Science.
Cat science.
All right. Thanks for watching. This is Decibel Lady Ada.
I proved that both me and you are alive, so that's what I...
Sometimes.
Yeah, at least for
And we don't, as you can tell, we, at this point, I don't think we can get venture capital or a bank loan because there's evidence that we can't be trusted with electronics.
This is on our anti-pitch deck.
This is why we can't have cat things.
They're all like talking on Sand Hill Road. They're like, we really wanted to invest in those like crazy goth kids, but like, did you see the animal abuse? Yeah.
No, we're the Uber of pets.com now. So, anyways, we're going to have probably a couple other shows. We're doing some recordings this weekend, so we'll have some fun shows coming up. But to support our shows and our company and all the weird things that we do, pick up a kit. That's how we pay the bills here. So thank you so much. And we'll see everybody on the next Desk of Lady Ada.
Thanks, everybody.
I'm going to go get the cat a therapist. So, sorry, cat.
That's probably true.
Well, it's like those wildlife shows back in the day where they would like tag and weigh the animal and then release the animal back out into the wild and then like watch them. It's all like that. So I'm gonna go make sure he's okay in his natural habitat,
he's fine. He's probably gonna throw up on the floor and then.
No, he just went back to sleep.
Yeah.
Okay.
All in a day of cat excitement. All right. Thanks for watching, everybody.
Later, folks.